At the same time, you see that this does not contain an interval, because the property of an interval is that if you take any two points, any two distinct points in it, then all the points lying between them are also inside that set. That is not true, because we are considering only irrationals. Okay? So you know that between any two irrationals, there is a ration. See, it's essentially the exciting properties or the wonderful properties that the real number system possesses that makes all these studies very interesting. Okay, so that's why I said that it's a when you go to work with real numbers, actually working in a world which is not too familiar to you, but it transcends your normal experiences. And that's the problem. Okay. So now we have plenty of or a better understanding of what null sets are. Now what we are going to explore is the converse of the theorem that we have proved. Namely, let me put it as a question. Let f bounded function. And our earlier experience has shown that if f is a Riemann integrable function, then the set of discontinuities form a null set. That's a fact. The set of discontinuities form a null set. And therefore, what we are going to ask is this. Suppose we know that the set of discontinuities form a null set. Is f Riemann integrable? Discontinuities. Of f denoted by d does this imply this is the question that we are going to ask. Okay. So we have to explore. So before we see, you should see the style in which the whole thing is getting developed. We very quickly keep visiting some examples, getting some feeling, and after the feeling we sort of formulate a sort of plausible conjecture and then trying to prove. This is the route along which the mathematics develops. It's not the way in which it usually done in a textbook or something. Well, we do a couple of a theorem and define something, prove a theorem, and then probably go to some examples. So that's not the way in which the subject is developed. Subject is developed certainly by the experience that you gain by looking at examples. That is why any aspiring student of mathematics should never hesitate to look at examples and put your hand on it and try to prove the various things that are the questions that come up from. So this is in fact, in this context, I think one of the books I suggest, I often do that, but I think I also would have said it earlier, you should look at this book, How to Solve It, by G. Poynter. You can download it. It's a beautiful book which every student of mathematics and teacher should necessarily read. And I believe that even anybody working in the area of science would derive a lot of clarity by reading this book, because it essentially dwells upon the mode of thinking in mathematics or mathematical subjects. Okay, so that's about it. I don't want to spend much time. So before we address this question and try to answer this, investigate this, look at an example. It's a beautiful example. This is something to do with the popcorn. It's called the popcorn function. Wow, somebody has named it because you can see that it's a suit. I believe that the nature of the function is that it just, at various rational points, the function props up. At all irrational points, it is 0. And it gives an impression that when you work on popcorn, making the popcorn, you can see it jumping. And maybe that's the reason for that. Here it is called popcorn function. Now let's define this function. We investigate this function a bit. Let define this as f of x this is equal to 1 at 0. It's equal to 1 by q at x equal to p by q. It is rational points where the common divisor of p and q is equal to 1. When you define this as 0, that's all rational points. So let us just quickly digress this. The function, it's not possible to draw the graph of the function, but at 0 and 1 it takes the value 1. Takes the value 1. And it is bounded by 1, it's non-negative function. And you see that at half it is 1 by 2. At 1/4 it is 1 by 4. At 3/4 this is 1/4. This is 1 by 2. This is 3/4. At 3/4 it is again 1 by 4, and so on. Okay, so you can actually see how the function works. If you take the point 1 by n or some m by n where the common divisor of m and n is equal to 1, then you see that the function is defined as 1 by. Okay. Okay. Now let us look at the properties of this function. When it needs I need to prove these things, that this function is something worth looking at, because essentially these kind of fascinating entities that you have or functions that you have makes or creates analysis. And you see that what one can prove is that f is continuous at all irrational points. F is discontinuous rational points. Both these statements require a proof. Now what happens is, if you take an irrational point, look at the decimal expansion of that. It lies between 0 and 1. It is of the form something like point a1, a2, etc., etc., etc. And because it's an irrational point, it is not an ending expansion that you have. So if you try to, you can actually get a sequence of rational points, something of the form by 10, a1, a2 by 100, etc., which in turn converges to 0. Okay, so you see that the properties, when it gets closer and closer to the irrational number, is that all the numbers become closer to 0. Okay, so you can actually write a very vivid proof of that, a very rigorous proof of that. So that is something for the rational points. Whereas at rational points, the function is discontinuous, because at rational points, certainly the value of the function is not equal to 0. So what happens? Suppose you take a point p by q, then the function, the value of the function is 1 by q, and you see, you take epsilon, say equal to 1 by, now you take any neighborhood of this point. Any neighborhood of this point p by q. What can you say? See, what is that to break continuity? What do you need? There exists an epsilon such that for every neighborhood of this, what is this? See, f is continuous if given epsilon there exists delta positive such that mod This is continuity. So the negation of this is that what you do is there exists an epsilon positive with the property that for every delta greater than 0, this does not imply this. Okay? This does not imply this. So that you can do by choosing epsilon equal to 1 by 2 to, you can easily work this out. So I leave it to you to work this out. So one should learn the art of making such arguments. So you can easily prove that these two facts you can prove. You need a little bit of careful writing up to get the proof. Now what we are interested in is F integrable. This is what we are going to investigate. Is F integrable in the sense of Riemann. Now let us start analyzing this. So what we are going to look at is the points of discontinuity. The points of discontinuity are all rational points and it's countable. Therefore, it is a null set. Therefore, we expect the function f to be Riemann integral. So we are essentially investigating whether you can write a proof for this conjecture. At the moment, it's a conjecture. So, anticipate that f is Riemann integral. Because the points of discontinuity of points of discontinuity of f is A. This is the one. Can you prove this? I mean, this is the question. Can you make use of the fact that the points of discontinuity is a null set? Can you use that to prove this result? So let us start working on it. So we make some observations. Let I be any open interval that intersects zero one. So it is something like this. So we have interval 0 1 and either like this or something like this. It intersects. That's a common point. Then what we can observe is that it contains an irrational point, and therefore there exists belonging to I intersection equal to 0. Therefore, what you can infer is that for any such interval, the function takes value 0 on that interval at some point, and therefore the minimum value is attained at some point on that interval. What does it mean? Well, the function is something that lies between 0 and 1. So it attains the minimum value at some point on that interval, which means that mi for the interval I, okay, this is equal to 0. This is the lower bound. Greatest lower bound of the function is 0. And consequently, this also means that L, P, F is equal to 0. Why L, P, where P is some partition of because partitions are intervals, okay, right? Therefore, on every interval of the type xi minus 1 to xi, you have a point where the function f vanishes, and therefore the minimum of the value the function picks up on that interval is 0. Therefore, you see that the lower sum corresponding to the partition is equal to 0. In fact, the lower sum corresponding to the partition of any partition is equal to 0. Not for a particular partition, for any partition. Okay. Now we want to analyze the points of discontinuity. So this is, so in the Riemann integral, if it were to exist, okay, if you write down the, see what we are, what is our strategy? Our strategy is to take the upper sum and the lower sum, or essentially fix an epsilon, and then show that there exists a partition, and for which UPF minus LPF is less than epsilon. So in this case, of course, LPF is 0 for any partition. Therefore, you need worry only about the UPF. Therefore, UPF is less than epsilon. Now, this is the thing that you have to prove. So, given epsilon positive, there exists a partition P such that UPF is this. So, given epsilon positive, does the a partition P of 0, 1 such that which is actually UPF minus LPF. If so, then it's clear that F is a Riemann integral.